Welcome to this lecture on combinatorics. Combinatorics is a branch of discrete mathematics that focuses on the study of arrangements of objects from finite sets that satisfy given constraints. So for example, if you consider the finite set of the 26 letters of our alphabet, a word, an English word, is an arrangement of some of these letters. Notice it's like a finite sequence since the order of the letters matter in the word. So in combinatorics, we consider three kinds of problems. The first kind is called existence problems. In this case, the question you're asking is there at least one arrangement satisfying some constraints? So in our example, we could ask, are there any English words that have exactly 3 letters in them, and these letters are all vowels? The answer to such questions is yes or no. These are existence problems. Now, a second kind of problems in combinatorics is the counting problem. Here the question is, how many arrangements satisfy given constraints? So for example, you could ask, how many English words have exactly 8 letters in them and have the same number of vowels and consonants? So the answer to this kind of problems is an integer, since we are counting the number of valid answers. Or it could be a list of these words, or these arrangements. In this case, the counting problem is really called an enumeration problem. The third kind of combinatorial problems are called optimization problems. In this case, the questions we're asking are of the form, among all of the arrangements that satisfy a given set of constraints, which arrangement is best according to some preference criteria? So for example, we could ask, what is the longest English word that has more vowels than consonants in it? So in this case, the set of constraints, there's only one constraint that all of the words must satisfy, is that they contain more vowels than consonants in them. And the preference criterion is that we prefer longer words. So the answer to this kind of questions is one of the arrangements. So in this course, we're only going to have time to look at the counting problem. This is a very important problem both in mathematics and in computer science. Remember, for example, that when we do the time complexity analysis of algorithms, what we're really doing is counting the number of instructions that get executed when the algorithm is run. So counting is very important. We're going to spend just a little time on it in this lecture. And it turns out that a few basic counting rules underlie all of combinatorics. And in this lecture, we are going to study 3 of these basic rules. So the first essential counting rule is called the product rule. I'm going to state it formally, and at the same time I'm going to illustrate it with a concrete example. Let's say that you've always dreamt of visiting Paris, and in particular of going to the top of the Eiffel Tower. So your task is that trip to the top of the Eiffel Tower. So if a task can be broken down into a sequence of case steps, so for example, in the case of a trip, the first step would be to get to the Chicago airport. And then the second step would be to fly from Chicago to Paris. The third step would be to get from the Paris airport to the Eiffel Tower. And the fourth step would be to go from the bottom of the Eiffel Tower to one of the intermediate levels. And the last step would be to go from that intermediate level all the way to the top. So here is an example of a task that can be broken down into a sequence of case steps. Now further assume that each of these case steps, S sub I, can be completed in a number of different ways. and that number is n sub I for each step s sub I. And this number of ways to complete each step is independent of how you executed or completed the previous steps. So again, let me use our example to illustrate this assumption. Let's say that you have 3 different ways of getting to the Chicago airport. You could either drive, you could take a cab, or you could fly from Appleton to Chicago. So you have 3 different ways of accomplishing the first step. And then for flying from Chicago to Paris Charles de Gaulle's airport, say maybe you found 5 possible itineraries. So you have 5 ways of completing that step. Now, say you're in the Paris airport, you have 2 ways to get to the Eiffel Tower, either by metro or by taxi cab. Now, once you're at the bottom of the tower, there are 4 elevators you can choose from to get to the intermediate level. And once you're at the intermediate level of the Eiffel Tower, you have 2 possibilities to get to the top. These are 2 different elevators. So these are the assumptions for the product rule. And here is the conclusion of the rule. It says, in that case, there are n1 times n2 times ... times nk ways to complete the overall task. Since the choice you make for how to complete one of these steps is completely independent of the other choices you make for the other steps, we can apply the product rule to compute the total number of ways you can get to the top of the Eiffel Tower. For every choice you make here for step 1, you have 5 choices for step 2. So just for the first 2 steps, the total number of ways is 3 times 5 or 15. And of course we can repeat this reasoning for the sequence of all 5 steps. So the final answer to the question is there are 240 different ways for you to get to the top of the Eiffel Tower. So this rule is called the product rule, since under the assumptions we can just multiply out all of the numbers of ways you have to accomplish all of the steps. Since there are many ways of stating the product rule, let me give you one that you should be familiar with because it uses the terminology of set theory. Let's say that you have a collection of k finite sets, and your task is to choose one of the elements of the Cartesian product of those k sets. Remember that the Cartesian product is the set of all the tuples of k elements. So one way to decompose this task of picking one of the elements of the Cartesian product is to first choose one element of set A1, then choose an element of set A2, etc., and finally choose an element of set AK. And the question is, how many ways are there to complete this task? Well, the answer is exactly the number of elements in the Cartesian product of the k sets. So it's the cardinality of this Cartesian product which is equal to the product of the cardinalities of all the sets in the collection of k sets. So this formulation of the product rule relies on the cardinality of the Cartesian product.